the assignment that is due today is 5.1. 5.1 is on the extreme value theorem. The extreme value theorem. Now, before we talk about the extreme value theorem, I do want to, let's do an AP question. So let's look at this one. Given the function f of x, maybe I need to move down. This is going to be a little bit larger. So given the function f of x equals x squared minus 4 divided by x minus 2 for values of x that are not 2. And f of x equals 1 is the other part of our piecewise for values of x that do equal 2. And then I want to know which of the following statements are true. Here is one. F has a limit at x equals 2. The next statement is f is continuous at x equals 2. And 3, f is differentiable at x equals 2. Okay, this is an AP question from a past test. We have 3 statements. I want to know which of those statements, if any, are true. Sasha. Sasha, any guesses? Mm-hmm. Okay. So you're saying that maybe that this function right here is differentiable when x equals 2. So Sasha, you're guessing that 3 is the answer? Any other guesses? Two? Is that Kata? Any other guesses? Let's look at the first one. First one says f has a limit as x approaches 2. Is there a way that we can use this piecewise or examine this piecewise? Is there a way we can do this to see whether there's a limit when x equals 2? If this is a non-calculator based question. Emerson, any ideas?
I guess like just plug in values close to 2.
Okay, if you plug in values close to 2, I guess you could see whether that is a legitimate way. It is a legitimate way to find out whether there's a limit. Is there anything I can do with this piece of the piecewise right here? Part of this piecewise says f of x equals x squared minus 4 over x minus 2, right? Part of our piecewise says that for values when x is not 2. Is there something I can do with this to help me examine whether I have a limit or not? In fact, specifically, can I calculate this limit as x approaches 2 for this function? Is there any way, any tools that we've learned of how to deal with that? Eleanor? Yeah, so what is a tool for solving this? If I want to know whether there's a limit when x approaches 2, which is literally this this statement here that I've said, that the limit is x approaches 2 of our function. Is there some way we can, what from our tools on limits, is there a way we can find the limit for this? All right, let's expand. I like that idea. Do you recognize this as a difference of squares? Yeah. So that means that I can rewrite this as, so I have the limit as x approaches 2 of what, if it's a difference of squares, Eleanor? And x minus 2, yeah. Which means that these can cancel out, right? Which means that I'm left with the limit as x approaches 2 of this x plus 2. To get what? Yeah. So there is a limit, and that limit is 4. When x gets closer and closer to 2 from either end, our y value gets closer and closer to 4. That happens only because we cancel them out. What if we couldn't cancel out this binomial? Wouldn't it mean that we have it when x is 2, wouldn't we have some type of infinite discontinuity? If it couldn't cancel out, that means we have an infinite discontinuity. If it does cancel out, then we just have a hole, right? In fact, we should be able to graph this. If this cancels out to this, then don't we just have y equals x plus 2, which is really just a secondary math 1 idea. How do you graph this? How do you graph this? Yeah, it's just linear, which means what? How do I graph it? Okay, rate of change of 1. So my slope is 1 up, 1 over, and what? Y-intercept is 2. So I'm going to go over here 2. And then we have 1 up, 1 over, 1 up, 1 over. We just have a line right here. But we found that because of this binomial canceling out here, that x cannot be what? It cannot equal 2. So at some point over here, we have when x is 2, we have a hole. And over here, what's this number here? Yeah, it's 4. We found it to be, that's our limit right there of 4. So this is 4 here. Now, if I look at this piecewise, it says here that x equals, when x is 2, my y is 1, which means if I wanted to finish graphing this, then this would be when x is 2, y is 1. So we have a dot here. Does that look more or less what the graph would look like from your understanding of a piecewise? Yes or no? Okay. So let's look at the graph that we created. Does our function have a limit when x is 2? Yeah, I agree with you. We'll say yes. All right. What about is f continuous when x is 2? No. What if this over here, what if when f of x equals 1, instead of when f of x equals 1, it was when f of x equals 4, or x values of 2? Wouldn't that mean then that this dot then, right here, that dot right there, let me make this transparent, that dot right there would be here, right? What kind of discontinuity is that? Yeah, that's a removable. It takes one single dot. If I had one, if this value here was f of x equals 4, that would take care of the problem and it would be continuous. But because it's not there, it's down here. Is f of s, is our function continuous? No, it's not continuous. No, continuity is defined, a simple definition of continuity is defined by if I can draw a line without lifting up my pen. Once I lift up my pen right here, then it's discontinuous. So we have a removable point of discontinuity when x is 2. All right, let's look at what are the different types of discontinuity. Okay, we have infinite. What's another one? We have a jump. What else? Removable. Okay, what else? Yeah. An oscillating point of discontinuity. All right, so then the third one, the third statement says f is differentiable when x is 2. Is this graph differentiable when x is 2? No. In fact, there are 4 different, so let's talk about not differentiable. There are 4, right? What are they? Okay, a corner. A corner is not differentiable. What else? A cusp. What else? A vertical tangent. And yeah, any point of discontinuity. Which is all of these over here. So is it differentiable? And why not? Yeah, it's because of discontinuity. Yep, we have a point of discontinuity. So the answer to this is no. So for this one, so which of the following statements are true? Only I, right? Or that one, that Roman numeral 1. That's the only one that is true in this case. Okay, moving on. We are going to be talking about, so the main idea today is the extreme value theorem. Before we talk about the extreme value theorem, I want to talk about what extreme values are, or what is called extrema. What are extreme values? What are extreme values, or what is called extrema? Well, consider a graph like, I don't know, like this. And these have a lot of different values along, in fact, there's infinite, this is a continuous line, so there are infinite values. And we could say something in between here that would indicate all the y values that are more or less average, right? This would be an average. Anything close to that would be considered average. Now, anything that gets further away from that, we're getting to extreme values. So this would be considered an extreme value. This would be considered an extreme value. This would be considered an extreme value. This one here as well. Any guesses what extreme values are? What's another word for this point here? Or this point here? Or this point here? When we get away from the average, we call that like a maximum point. So when we talk about extreme values, we are talking about maximums and minimums. Those are extreme values. Now there are different, I mean, I could say that this is a maximum. And the way that we define a maximum is by looking at the points that are immediately around it. And so this would be a maximum point. But if I look at all of the graph here, then this point right here is the maximum it's the most maximum. And so there's got to be some verbiage to differentiate the difference between the most maximum and other maximums that are defined just by looking at the points around it. And there is that we have some verbiage where this point right here, we would call this the absolute maximum. We could also call it a global maximum. Now, I'd love to say that one is used more often than another, but they're not. I've seen both of these equally used on an AP test. An absolute maximum and a global maximum are the same thing. It means they are the most maximum. Any guesses what this point right here would be called then? Yeah, it'd be an absolute minimum or a global minimum. This would be an absolute minimum or a global minimum. Now, what do we call it if it's a maximum, but not the most maximum? Defined by looking at the points just around it, that point is the highest out of all the points around it. It's still going to be a maximum, but it's not an absolute maximum or a global maximum. We call it a local. Good job. It's a local max or a relative max. So this point right here is also, because it's not the most maximum, we also call this point right here a local max and a relative max. Which means this point right here would be what? Yeah, it's a local minimum or a relative minimum. Now there's one I missed here. You guys see which one I missed? Did I miss any maxes or mins? Where is it? Yeah, it's right here in between. Yeah, that one is, because when we're talking about a local max or a local min, we're talking about it's a max or a min based upon the points that are around it. And based upon the points that are around this point, it is the lowest point of those local points. So that would be another, in this case, we have another local min or a relative min. All right, so let's talk about then, if we know then what an extreme value is, well, what is the extreme value theorem? And before I define the extreme value theorem, I want to, because it's a relatively easy idea, and so I don't want to get too wordy. I'm going to explain it first in as simplest of terms that I can think of, and then I'll define it. Now, the idea is that for any graph that is closed, which means that endpoints are included, and it's continuous, then it's guaranteed that you have a maximum and you have a minimum. One more time. If I have some interval that is closed, which means that I have that the endpoints are included and it's continuous, it guarantees that I have a maximum and a minimum point. So in this case, this would be my max, my global max, and this would be my global min. Okay, so we're going to define it now. Let's use a different color. How about blue? The extreme value theorem. If f is continuous on a closed interval, we'll say from A to B, then f has both a maximum and a minimum value. Okay, so I'm just going to draw some pictures. Whether you choose to add these to your notes or not is up to you. But here is the idea. So here's from A to B. And I have a closed continuous line or continuous graph that guarantees a max and a min. Here's another possibility. If this is closed and continuous, it guarantees a max and a min. Or let's do two more. From A to B. Something like that. Guarantees a max, guarantees a min. If it's closed and continuous, it guarantees a max and a min. Questions about the extreme value theorem? Y equals that's a good question. What if I have something like this? 1, 2, and I have this line that's solid. Then my maximum is 2 and my minimum is 2. Where is it? It's everywhere in this case. But you are still guaranteed a maximum point and a minimum point. They just, in this case, turns out to be the same. Okay, so let's move on. Let's do another graph. I'm gonna zoom in. Based upon the extreme value theorem, am I guaranteed a max and a min in this case?
No.
Why not?
Well, A, it's not continuous, and B, you don't have a fixed point. in this graph.
And it's not closed either, right? And we're not closed, it just keeps on going. So it's not closed here, it's not closed here, it is not continuous there. So we are not guaranteed. In this case, we are not guaranteed a maximum and a minimum because this is not closed and it's not continuous. So we are not guaranteed a max and a min, or I should say, or a min, based on the extreme value theorem because this curve is not closed and not continuous. Well, the extreme value theorem guarantees both.
Okay.
And so does it mean we don't have a max and a min? Do we have a maximum point here?
Yes. Assuming if we're to assume that the arrows go off and they don't ever.
So let's consider global. Let's consider a global max. Do we have a global max? Let's say that this is, I don't know, 2, and this is, I don't know, 8. Do we have a global max?
But we have a hole there, so we still consider. Would we just consider the point as any point approaching?
So is my maximum point, it looks like I'm really close to 8, right? Is the maximum 7.9? Or is it 7.99? Or is it 7.99999? Or 7.9999999? You know, what can you tell me a maximum that I have?
I can tell you a local one, but
not a global one. Yeah, you can't add enough 9s to represent what that is. We get really, really close to 9. We get infinitely close to 9. And so we can't say a number specifically. I can't give you a maximum number. So there's not a global maximum. Is there a global minimum? No. This indicates that it just keeps on going down forever and ever, right? So we'd say that the minimum, it goes all the way to negative infinity, which isn't a real number, it's a concept. We say we go to the lowest number you can possibly think of, and then it keeps on going below that as well. So it's not a stopping point. So there's no minimum, it just keeps on going down, and no maximum, but for different reasons. No maximum because I can't get there. I can't quite get to 8. There's always an extra 9 I can add. And then here, well, we're just shooting off to negative infinity, so there's no minimum. Okay. All right, so let's talk about this. This is a pretty important idea. How would you find any ideas of how, in using calculus, how we'd find a maximum, not necessarily a global maximum, but how we'd find a maximum and how we'd find a minimum? I guess this is a minimum, since it's the lowest point from the left and the right side. Can you guys think of a way, think of calculus. We're in a calculus class. And calculus, the calculus class seems to always integrate what? A derivative. Can you think of some way that we could use our ideas of calculus to find a maximum or a minimum?
As x approaches to.
When x approaches to.
Local minimum.
So are you thinking more like this one here specifically? I'm talking about in general.
Okay.
In general, how could we use a derivative to find a maximum or a minimum? Yeah, slope of 0. Yeah, does that make sense that any maximum, let's draw a graph. That if I have some graph like this, does that make sense that any maximum point that my slope is going to be 0, or a minimum point, I'm also going to have a slope of 0? Is that logical? So in calculus, we can find any maximum or minimum point by finding the derivative and then setting the derivative to 0. Do you think that if I find where my slope is 0, that guarantees either I have a maximum or a minimum? If I find the derivative and I set the derivative to 0, does that guarantee that I have either a maximum or a minimum? It doesn't. No. In fact, I'm going to draw out all the different possibilities for you. If I find the derivative, if I find where the derivative equals 0, I find the derivative, I set the derivative to 0, I solve for x, that tells me where. It doesn't tell me what the maximum is or maximum or minimum. It tells me where I have, I'm going to actually use the word stationary point. It tells me where I have a stationary point. Now, here are the different possibilities of a stationary point. A stationary point could look like this, where I'd have a what? What would that be? What kind of stationary point would that be where my slope is 0? What is that? It's a maximum. Yeah, this is our maximum point. That gives me a max. If I have something like this, what does that tell me? If my slope here is 0, that would tell me I have a minimum. Now let's look at this relationship too. On the left-hand side, my slope is what? From this, at this point where my slope is 0. On the left-hand side, my slope is what? Yeah, it's positive. I have a slope that is positive followed by a negative. If I have a slope where it's positive followed by a negative, then I have a maximum. If I have a slope, what's this slope here? That's a negative slope. If I have a negative slope followed by a, what kind of slope is this? A positive, then that means I have a minimum. Now let's consider some other possibilities, because I could also have something, I'm going to actually zoom in. I could also have something that looks like this or like this. And this right here, that is my stationary point where my slope is 0. Where my slope is 0. Now let's look at, on the left-hand side, what's my slope? Yeah, it's positive, followed by a, it's still positive. So if I have a positive followed by a positive, that is not a maximum or a minimum. In fact, what do we call this point right here? We call it an inflection point. Yeah, look at the concavity. Look at the concavity over here. Concave up or concave down over here? What's the concavity on the left-hand side? concave down, followed by concave up. And that's how you define an inflection point, when the concavity changes. So this is a stationary inflection point. Over here, let's look at this. This is also another stationary inflection point. What's the slope over here on the left-hand side of my stationary inflection? Negative followed by a negative. These are called stationary inflection points. So I'm going to ask the question again. If I find the derivative, I set the derivative to 0 and solve for x. Does that guarantee that I found a maximum or a minimum? No, it could be a stationary inflection point. It could be one of these. That is a possibility. All right, when I try to find a maximum and min, let's go down. If I'm going too fast, let me know. These are really important ideas. The max is a positive followed by a negative. A min is a negative followed by a positive. And then we have stationary points where we have a positive followed by a positive or a negative followed by a negative. Okay, how do we find what is called extrema? How do we find extrema? What is an extrema? What do I mean by extrema? What is an extreme value? Yep, it's a max or a min. I'm specifically talking about a max or a min. How do we find extrema? Well, one technique is to take the derivative and set it to 0 and then solve for x. We also need to consider the end points. The end points could be a max or a min. Or we also should consider any point that's not differentiable. Any point that is not differentiable. Why does that matter? What point could be a maximum point and also not differentiable? Yeah, a cusp, but we could have a cusp where we have a maximum point, but it's also not differentiable. So we need to consider those points that are not differentiable. Question? Oh. Okay, let's do an example. I think I'll just go to the top. If I'm going too fast, let me know. Mr. Hall is about to write that down. No, just say, Mr. Hall, go back. Okay, let's move over here. Here's my example. I want to find all the local and global extrema. And my function is 1/3 x cubed. That's ugly. Minus 5/2 x squared minus 14x plus 7. I want to find the extrema without a calculator. Kyle, where would I start? How do I find an extrema? How do I find a maximum and a min without using a calculator? Emma, any ideas? Huh? Yeah, we find, in fact, if all else fails, find the derivative because this is a calculus class. Yeah, so in fact, that's one of our suggested ideas, right? Down here, what we talked about previously is to find these maximums and mins, we just find the derivative and set it to 0. So let's go ahead and do that. Emma, can you help me with this? So the derivative of f of x is what? Not sure how to take the derivative of this. It doesn't look like a fancy way. It just looks like the power rule.
Is it 3 times 1/3 x squared?
Yep. So what does this become? Yeah, isn't that just one, Emma?
Yeah.
Okay, so I'm just gonna cheat. That's okay. This is just our x squared. Okay, what about this?
What is the like? Does the negative go? Does it stay with the 5/2 or is it?
So it isn't our power rule when I have a times x to the power of n, and then what is the power rule?
It's a and x to the power of n-1.
What if a was negative?
It just stays like that.
Yeah, it just stays there. Yeah, it just stays like that. Okay, so Emma, how do I take the derivative of this?
So that's 2 times negative 5/2. And then just times x.
What does this become here?
Negative 14.
Isn't 2 the same thing as 2 over 1?
Yeah.
So what does this become?
-5.
Yeah, is this just -5? Because 2 divided by 2 is just 1. Just like, or you could multiply if you want. That would give a -10 over 2, which is still 5, -5. So I'm going to cheat. Guess it doesn't matter. Maybe I should have left it. I don't know. All right, so I have 5x. And then Emma, what does that become?
Is that just -14?
Correct, -14. And then Emma, this one?
There's no, like, it has no value.
It does have a slope.
Right, but doesn't it, like, not have
So the slope, if I just look at this piece right here and I consider that this is my function of y equals 7, which is a graph that looks 1, 2, 3, 4, 5, 6, 7. It's a line like this. What's the slope?
0?
Yeah, it's just 0. So I could write +0, but that's redundant. You don't need to do that. So, but there is a slope. There's a slope for 7 and it's 0. So I'm just gonna forget about it. Okay, now what do I do? I'm trying to find the local maximum and mins, local and global. What's the next step, Emma?
I don't know on that.
Well, what was that first number 1? What was that suggestion here?
Oh, set the differential to 0.
Yeah, yep. So if our derivative is this, and this means the slope right here. So I'm going to make that 0. So I have 0 equals x squared minus 5x minus 14. Now I'm trying to find, it says find all of the local, I'm not finding what the max and mins are. I'm trying to find where they are. So how do I find where they are? Not sure how to solve for x here.
Oh, well, yeah, are you just trying to get
Is that how we solve for this? There's something important that we learned in secondary math 2. We could use the quadratic formula. We could complete the square. We could factor. Is this even factorable? Is it factorable? Is this factorable? To what? Plus 2 and x minus 7. Okay. So what are my x's so that I get 0 over here? So I have 0 equals 0. Yep. So x equals -2 and x equals 7. So does that guarantee one of these is a max and one is a min?
No.
No. I know there's a stationary point. I know my slope is at 0 when x is -2 or 7. I know my slope is 0, but I don't know. It could be a stationary inflection point. It could be a max. It could be a min. So how would we go about, what would we do at this point to find out whether these are max or mins or stationary points? Well, this was a really important idea over here. If we know what the sign is on both sides, wouldn't that tell us whether it's a max, a min, or a stationary inflection point? So we're going to use what's called a sign diagram. To find out what kind of stationary point we have, we're going to use what is called a sign diagram. To find out, oops, that's messy. To find out what type of stationary point we have, we use a sign diagram. We're literally trying to find out whether we have a positive followed by a negative, or a negative followed by a positive, or a positive followed by a positive, or a negative followed by a negative. So we're going to do a sign diagram. Here's my line here. I'm going to identify these points of -2 and 7. Now I'm going to use this graph here. This equation right here tells me what the slope is. So let's use this. In fact, this is the same equation here. I just factored it. And we're going to, all I care about is the sign. All I care about is the sign. So let's use this equation. Let's just make this f of x right here. Actually, let's make that f of x, f prime of x, I should say. And then I'm going to determine whether it's positive over here or negative, positive or negative, positive or negative. Did you guys see what I'm trying to do? How do I figure out whether it's positive or negative over here? Well, pick a value over here. What's a value that's below -2? Okay, let's try -3. Now, all I care about is the sign. If I plug in -3 here and here, is this part here positive or negative? What is it? It's negative. So I have a negative, and then if I plug in -3 over here, that's a negative as well. Okay, let me get rid of that. Okay, so that gives me a negative followed by a negative. What is a negative times a negative? Okay, that's a positive. Now we want to find out whether this interval has a positive slope or a negative slope. So what's a value, a number, any number in between -2 and 7? Right, 0. If I plug it, so I want to try, let's try x equals 0. If I plug 0 in here, is that positive or negative? Okay, I have positive. If I plug in 0 over here, positive or negative? Negative. What's a positive times a negative? It means that I have a negative slope between -2 and 7. Let's do the same thing over here. What's a value, a number greater than 7? 8. Okay, so try x equals 8. If I plug in 8 over here, is that positive or negative? That's a positive. If I plug 8 in here, is that positive or negative? Positive. What's a positive times a positive? Okay, what does that say is happening when x is -2? That's a maximum. We have a positive slope, followed by a negative slope. That means that's a positive point, a maximum point. So x equals -2 is a max. What's happening when x is 7? Yeah, we have a negative slope here, a negative slope. So negative slope, negative, 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 followed by a positive slope. So positive, positive, positive. That means we have a minimum point right there. So x equals 7 is a min. Can we find out what kind of max and mins? Are these local or global? When does it stop being positive over here? When does the slope stop being positive for this interval over here? It doesn't. It's always positive, right? It's going to be positive all the way to -infinity. So we have a graph all the way from -infinity that goes positive, 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 positive to this maximum point here. Then it becomes negative, 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 negative to this point here, and then becomes positive. When does it stop becoming positive over here? It doesn't. We go all the way to infinity there. So are these maximum, are the local or global max and mins? They're what? They're local. These are local. Local. For both of them. Everybody good? Okay, continuing on. Let's do another one. Is this painful? Or is it fun? If you think it's painful, then have a better attitude. Math is fun. Math is challenging. Math has a tendency to make us feel dumb, but there's something really cool, something euphoric when you finally get it. It's like, wow, that's so cool. Okay, here's the next one. I want to find all absolute and relative extrema for our piecewise function 5 minus 2x squared for values of x that are less than or equal to 1, or the other piece of my piecewise is when x plus 2 for x values that are greater than 1. Are you stuck? And Sasha is on her phone. Sasha, I want you paying attention. Are you stuck? Or do you want some more think time? Kata, are you stuck? So if I'm trying to find an extrema, how do I do that? Okay, let's find the derivative. So let's find the derivative of each piece. So I have the derivative for the first piece when f of g of x equals 5 minus 2x squared. That becomes what? Negative 4x. Okay, good. And so Is there a way that I can find when I have a zero slope? Yeah. Make that 0. And so x equals what? 0, yeah. When x is 0, I have a 0 slope. What about this piece over here, this x plus 2? If I take the derivative of this other piece over here, the derivative of this, what do I get? Which means what?
Well, 0 can't equal 1, so we don't have 1 for that.
Yeah. Does it make sense? Let me rewrite this the way you would see it in secondary math 1. We'd just see it as y equals x plus 2. Based upon your understanding of y equals mx plus b, what is the slope? It's 1. And we calculated it using calculus as well, that it's 1. So Riley said that this can never, over here, this piece over here, it doesn't have a 0 slope anywhere because the slope is always going to be 1. So, I mean, I guess we could draw it out. This is quadratic, so our graph is gonna, the first part is quadratic and it's upside down because our leading coefficient is negative, so it's an upside down. It's going to be concave down, right? From our secondary math 2 understanding of quadratics, we should have something like this. The graph should look like this, followed by this line that goes off like that. Is that sort of your understanding of what that would look like? More or less? Okay. So let's try to figure out. So I'm going to use some verbiage that I haven't used before. This one, I'm going to use this verbiage called a critical point. A critical point is not necessarily an extrema. It's a point we need to examine. A critical point is not an extrema, necessarily an extrema, but it's a point we need to examine. A critical point, in fact, I'll zoom in on this. A critical point is a point that could be an extrema. So it seems like with this transition between this part of our piecewise and this part of our piecewise, that there could be a maximum or a minimum when in fact x equals 1. Now I'm using a different x equals 1. This isn't x equals 1. That's not what I'm referring to, the slope. I'm referring to when x is 1. That's a critical point when there's a transition from one graph to the next. So when I use, what's that called? The graph where I determine whether I have plus or minus or whatever. What's that kind of graph called? It's called a sign diagram. So this is my sign diagram. I'm spelling it wrong. Diagram. And I have two critical points that I see. One is when x is 0. That's what I found using the first piece of my piecewise. That's a critical point. When x is 0. And also because of that transition point from one graph to the next, not this slope here, that's a different one. That is also a critical point, that transition from one graph to the next. All right, how do I find what kind of sign I have on this side? Is it possible somewhere in between that the graph, I have another maximum? Is that possible? No, I would have found it. By taking the derivative, I would have found that other point. So it's impossible. There is no other, I don't have any other stationary points other than 0 and 1. Okay, so how do I find out what kind of sign is happening over here on this side? Yeah, let's plug in -1, that's below 0. So let's try x equals -1. Now, which graph am I going to use? Am I going to use this one here or this one here, the left or the right side? Am I going to use this one or this one to find out what the sign is? The left one, because the left one, that tells me the slope for any x value below 1. So we're going to try that. I'm going to plug in -1 here. What do I get when I plug in -1? Is it +5? It's a +4. It's +4. And I don't really care. I don't really care what the slope is. I just want to know whether it's positive or negative. So it's positive, right? Here, let me use red. It's positive. All right. So what about in between here, between 0 and 1? Which derivative do I use, the left or the right? The left again, because the left equation is for all x values below 1. What do you want to try? Try what? Try what for x? Try 0, try x equals 0.5. Okay. So if I plug in 0.5 into this equation here, do I get a positive or negative slope? I get a -2 or a negative slope. So I'll just indicate that here, negative. And then what kind of slope do I have on this side? Okay, I use the right equation, which means that the slope is always going to be +1 on the right-hand side. So this is going to be positive. What does that say is happening when x is 0? It's a maximum. I have a positive slope here, followed by a negative slope. That's a maximum point. And then what about when x is 1? So negative, 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 and then a positive, positive, positive. That's a minimum. So we have, so x equals 0 is so positive, positive, negative, negative is a maximum, is a max, and x equals 1 is a min. Can we find out whether whether it's an absolute max or min, or whether we're talking about relative? Is it relative or absolute? It's relative. Both? When does this left-hand side, when does this positive slope, when does it stop being positive to the left of 0? It's always going to be positive, right? All the way to that point, and then it becomes negative, and then becomes positive here forever.
Well, unless specified by a piecewise function, would you ever even get a global maximum or minimum?
Yeah, because what if I say that this is limited not for all x values above 1, but what if instead of this piece right here, I said it's for x values between 1 and, I don't know, 8.
But
right?
Unless we have that, we're not, assignment diagram will always show us that we don't have.
Yeah. Okay, so these are going to be relative, both of them. Okay, next one. Am I going too fast? Not like Sasha cares. She's just going to be on her phone all day. So I want to find all of the global and local extrema. Sasha, would it help if I held your phone for you? Can you be responsible with it? Thank you. I want to find the global and local extrema for h of x equals x over 1 plus x squared. Sasha, what do I do? So I'm going to find the derivative of this h of x. How do I do that? How do you do it? Even if you forgot the name of it, do you remember how to do it? Yep. Low to high minus high to low over low, low. That's the quotient rule. So low d high, what's the derivative of the high? Yeah, 1 minus high d low, what's the derivative of the low part? 2x over low, low. Sasha, does that look right to you?
Yes.
Okay, now what? What do we do now? How do I find an extrema? How do I find the extrema? Yeah, let's make this equal to 0. We want to know where means our x values, where we have a slope of 0. So I have 0 equals 1 plus x squared times 1 minus 2x squared. Are you okay with that?
Yeah.
Over 1 plus x squared all squared. Okay. How do we solve for this? How do we solve for this? Josh, any ideas of how to solve for this? Josh, it looks pretty ugly. I'm not sure. What do we do? How do we solve for this? How do we find out what x equals? That will give us 0 over here. Like the bottom part? Yeah. What if, Josh, what if I just multiply both sides by 1 plus x squared squared? 1 plus x squared squared. What happens over on the right-hand side? Yeah, this divided by this is just 1. I'm left with one of these, 1 plus x squared. Actually, I don't like the, doesn't seem very dark. Use purple. One of these, 1 plus x squared minus 2x squared. And Josh, what happens to the left-hand side? What does this become? 0. Yeah, how nice is that? It didn't have to be that scary. The denominator just cancels out because we're the other side equals 0. So if I just multiply by the denominator, it goes away. I had a student a couple of years ago that said, Mr. Hall, that's just wishing away your problems. But in fact, it works mathematically. Right now, what? What do I do now? Sasha. Sasha, maybe you need to get back on your phone. Okay, any idea of what to do at this point? Yeah, let's combine like terms. In fact, the parentheses, what we're distributing is this implied 1 in the front. If I distribute the implied 1, nothing changes. Who owns this negative right here? The 2. So I don't distribute the negative, correct? Because the negative belongs to the 2, not to the parentheses. Agreed? Okay, so if I distribute the implied 1 in the front here, then that's going to give me 1 plus x squared minus 2x squared. And then was that Chris that said combine like terms? Good job, Chris. So if I combine my like terms, what do I get? How many x's do I have? I just have, yeah, negative x squared plus 1. Does that look right? Okay, now what? Subtract, okay. We can say, yeah, Friday, a student said, Mr. All, don't we have a difference of squares? And we do, but we can do it the other way as well. We can subtract 1 from both sides. That gives me negative 1 equals negative x squared. Now what? Yeah, if I multiply or divide by a negative number, it switches the signs. That gives me x squared equals 1. Now what? Yeah. That gives me x equals plus or minus 1. We call these critical points. I call them critical points because they could be, they're a point of interest. They may be maximums and minimums, or they may be something else. It's something that I have to examine. How do I examine 1 and negative 1 to see if I have a max or a min? How do I examine 1 and negative 1? These are my critical points. How do I examine these to determine whether they are maximums or minimums? We need to use a sign diagram. Yep, we need to use a sign diagram. So use a sign diagram. Again, use a sign diagram where we have negative 1 here and 1 here. And I suppose it would be helpful if I went back up and we got our function. We found the derivative already here with this mess here. Right? Didn't we already find this? Right there? Okay, how do I find what my sign is to the left of negative 1? Say that again. What is a value less than negative 1? Okay, so try x equals negative 2. If I plug in anything in the denominator, isn't that always going to be positive? Okay, so the denominator is positive, and then the numerator, this piece here is going to be, actually I think it'd actually be more helpful if I use this other piece that I simplified. Didn't we simplify the numerator to be this? Let's use that in our numerator. We simplified this already to give us this. So let's just put that back in. All right, so the denominator is positive. The numerator is what? If I plug in negative 2, what does that give me in the numerator? Yeah, so that's going to give me a negative. What's a negative divided by a positive? It's a negative. So this is going to be negative here. All right, what about in between here, this interval? Okay, let's try 0. Try x equals 0. Again, anytime, whatever I plug in the denominator, it'll always be positive because it's going to be squared. So the denominator is always going to be positive. And then the numerator, if I plug in 0 here, it's positive. What's a positive divided by a positive? Positive, okay. And then over here, louder. 2. Okay, we're going to try x equals 2. Again, anything I plug into the denominator will always be positive. And in the numerator, I plug in a 2. It's going to be negative. What's a negative divided by a positive? A negative. So what does that say about x equals -1? What is happening when x is -1? It's a minimum. Yeah, we have a slope that's negative, so the graph is negative, 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 and then it becomes positive. So that's going to be a minimum. X equals -1 is a minimum. What happens when x is 1? It's a maximum. So I find, let's zoom out so I can see some, well, so I know that x equals -1 is a min, and then x equals 1 is a max. Do we know whether these are global or whether they're local? Yeah, they're local. Yeah, because these intervals continue out forever to infinity, because that's what our graph is. There's no stopping point. So these are local, both of them.